I suggest we get started to yet another doublet of lectures for this morning. We continue yesterday's discussion where you became an expert on conformal field theory methods. So yesterday's discussion started from concrete observation on the Polyakov action and its symmetries. We were seeing already 2 lectures ago that the Polyakov action enjoys a variety of symmetries that allow us to completely gauge fix the metric to virtually any form that we like. There were these 2 diffeomorphism degrees of freedom, one diffeomorphism for tau and sigma, and furthermore Weyl transformations, which are defined to only rescale the metric and to do nothing else. And the gauge fixing of the metric into our favorite form, say 2-dimensional Minkowski one, it still leaves a residual gauge freedom. Namely, among this gigantic class of 2 variable diffeomorphisms, there is a set of measure 0 of 1 variable diffeomorphisms that rescale the metric, like preserving the 2x2 matrix structure. And those 1 variable diffeomorphisms you can undo via a Weyl transformation. And if a diffeomorphism just rescales the metric, it's called a conformal transformation, not only in string theory in 2 dimensions, but in general space-time dimensions. So it's the conformal transformations that can be undone by a Weyl transformation, and they thereby preserve the gauge-fixed form of the Polyakov action. Well, strictly speaking, you can gauge fix the metric to something else, and conformal transformations will still appear as the residual gauge symmetry. So all this to say, the worldsheet description of closed bosonic strings enjoys conformal symmetry, and in 2 dimensions, this is extremely powerful, because unlike conformal symmetry in higher D, the group is infinite dimensional in 2 dimensions. And one way to organize this richness of conformal transformations is change coordinates either into the light cone one or something related, and then conformal transformations are the meromorphic maps. Or strictly speaking, there are 2 infinite towers of conformal transformations. The first such infinite tower is meromorphic functions of Z, and the other one anti-meromorphic functions of Z bar. Yeah, it's always nice when you have some meromorphic functions in the game, because then you can borrow various theorems from complex analysis, and I gave some samples yesterday of how you can take advantage in practical calculations, both of the Cauchy theorem to evaluate complex contour integrals, and also using the fact that complex contour integrals are homotopy invariant if your integrand is meromorphic and if you promise to not cross over poles. And here I'm squeezing 2 transformations into 1 equation. We first of all complexified the proper time tau on the worldsheet yesterday. So this T is Euclidean worldsheet time. And this allows you to form a complex combination out of the spatial coordinate sigma and time. And starting from that complex combination, we looked at the exponential map that takes you from the cylinder, the more intuitive description of a string worldsheet, onto the complex plane, which may have looked surprising at first glance, but I really like the complex plane because it first of all automatizes the periodicity property for closed strings, where sigma is as good as sigma plus 2 pi, and this is automatic in this variable choice. And another nice feature is that infinite past can compactify to a point, in that case the origin. And if you think of Z and Z bar as living on the Riemann sphere, namely complex plane plus point at infinity added, then also infinite future is getting compactified. So these are very convenient coordinates to work with. Then I delved into a discussion of so-called conformal primary fields. Initially, I defined them through their transformation law, waving my hands that this is somewhat comparable to introducing tensors into GR. So a conformal primary, what it does for its living, under conformal transformation, it's supposed to pick up a prescribed power of the respective Jacobian if you do meromorphic transformation zeta of Z and an antimeromorphic transformation zeta bar of Z bar. So this was meant to generalize the chain rule, which we saw identifies that derivative of the free boson as a conformal primary of weight 1, 0. And from that example, I hope it's somewhat intuitive. We should also have terminology to talk about cases where you have a higher number of such Jacobian factors. So that's what a conformal primary is doing by its definition. And how do we work with them? How do we take advantage of this concept for the purpose of bosonic strings? You can encode this transformation law in a very different way, namely through the interaction of phi with the energy momentum tensor. So what does the energy momentum tensor have to do with all that? Well, the energy momentum tensor is part of the Noether currents for all the conserved currents to the meromorphic transformations. And therefore, if you know how a field interacts with T, then you can deduce its conformal transformation properties. And the energy momentum way of stating that transformation is as follows. This is a so-called operator product expansion. I realize I'm not fully consistent in how I'm writing it down. Since the energy momentum tensor splits into one holomorphic, meromorphic component T and an antimeromorphic one T bar, I am taking the liberty to suppress the H bar index here. There's an analogous equation when you take the antimeromorphic component, T bar will then be sensitive to H bar, the second subscript here. So if you wish, I'm giving you here the chiral version of the OPE that was derived yesterday. You can recognize or diagnose this transformation law by checking if a field that you meet on the street has the following singularity structure with the energy momentum tensor. So if you find that singularities are no worse than double pole, and if you furthermore find these relative factors h and 1 between the undifferentiated field and the first derivative, then you are in business. This property implies that whatever phi is, that conformal transformations will act like such. So this is the direction of the logic that we will apply today. Suppose you have a field where it's out of reach to compute the conformal transformation property directly. Then it's good enough to study its interaction with the energy momentum tensor. So this is what we will do massively, using the concrete realization of T in case of the free boson. And just to be clear, in more general conformal field theories in 2D, which may not even have an action functional description, this OPE story still remains valid, or also the definition here. So there is a huge space of possible two-dimensional CFTs, and we are at the moment looking at the particular one, namely that of the free boson. So this OPE methodology, and in particular this equation here, is universal to all the 2D CFTs. And similarly, there is a universal relation how T is OPEing with T, where we saw yesterday that T is not a conformal primary field, and the obstruction to be primary was a quadruple pole, where the residue has the nickname central charge. And as I said, there's a huge collection of two-dimensional CFTs, and you can characterize them by their central charge and by the conformal primary fields. So the CFT data, so to say, is to state the value of C along with all the H and H bars of the conformal primary fields therein. Yeah, so here for the free boson we have central charge D, like the number of space-time dimensions. So each direction contributes 1 unit of central charge. And more generally, if you build a larger CFT by tensoring together some decoupled CFTs, what happens is that you add up the central charges. So it's a crude way of counting the number of degrees of freedom with some weight factors. Yeah, to make connection with the main plans for today, I still owe you a construction of the string spectrum and identification of the graviton. And a key player to do so is the plane wave, this exponential of the free boson, which by OPEing it with T turns out to have these conformal dimensions. So to get there, you need this Wick theorem, how you deal with OPEs when they are normal ordered products, and maybe a bit of combinatorics. Perhaps this is yet another exercise you should do for yourself at some point. And just to review, these normal ordering columns simply mean don't even think about doing OPEs among the enclosed fields. This is in many cases evident. Nobody wants to have a 1 over 0. But yeah, the formal way of saying where to not OPE is to put normal ordering columns. Yeah, I think that's it for the review. Any questions before we construct spectra? Okay, we are still in this lengthy section 2. We should get out of it within the next hour. Okay, and the states in the spectrum will enter through so-called vertex operators to be defined here. So a general dictionary that I will use all the time is the so-called state operator correspondence. So when you heard spectrum, then you probably expected me to give you a couple of Hilbert space vectors, states which may appear in a notation like such. And in CFTs, there is a one-to-one state operator map. Namely, given a state, then I can always find a field such that the asymptotic value of the field as at infinite past creates that state. So let's call that corresponding field phi psi. So this is a field on the world sheet. And I guess it's easy to follow one direction of the dictionary. If I already know a field, then of course I also know its asymptotics at the origin. And then I get a well-defined psi out of that map. But this also works in the other direction. Given a state, this is already enough to learn about the field. Maybe this requires an explanation in 2 steps. This equation tells you that knowing the state tells you about the field at the origin. But then, knowing the field elsewhere, away from the origin, this is a matter of conformal symmetry. So roughly speaking, you exponentiate the translation operator, which is L minus 1, and you get the field also elsewhere. Yeah, so all this to say, when the goal is to construct the spectrum, you have the free choice whether you construct Hilbert space vectors or whether you construct conformal fields. And the important intuition, which will also be crucial for scattering amplitudes later on, you can think of this as being an asymptotic state. Because what happens here is evaluation at infinite past. It's a little bit like having some field excitation far, far away in infinite past. Maybe there's a similar notion that you were told about in QFT when interacting QFTs were introduced in your course back then. So this is the intuition behind the state operator correspondence. Asymptotic states. using once more the fact that the origin in Z is infinite past. Okay, then I owe you some minimal explanation of this state here. This is vacuum state, and let's say the key properties that you need to know about it is that it's annihilated by various energy momentum tensor modes. It would be tempting to say maybe it's annihilated by all of them, but that's in fact too much. What suffices is that the matrix elements of the energy momentum tensor are zero, and it's good enough if half of the modes roughly eliminate the vacuum. Okay, I'm doing a little bit more than half. L0 is borderline, and L minus 1 seems to already be in the other half. But remember, there was this subalgebra SL2C with 6 generators, which included L plus minus 1 and L0. So the inclusion of L minus 1 means the vacuum is SL2C invariant. Okay, so with these preliminaries, I can give you a couple of inviting examples for state operator correspondence. For instance, the energy momentum tensor, which is all over the place. What's its state correspondent? Let's just look what happens if I evaluate that limit here. So remember that T had a Laurent expansion in terms of exactly these L modes, and we can see upon insertion of the Laurent expansion that the properties of the vacuum are in fact life-saving. I mean, there is this Laurent expansion for T, where all integer powers of Z occur. And imagine we didn't have these annihilation conditions. You would have infinitely many terms where you catch a massive 1 over 0. So at a very pragmatic level, this simply means that you don't need to worry about divergences as you evaluate that limit. Needless to say that you first exploit who is annihilating the vacuum and then play around with Z. Okay, so everything divergent is cut out. Then positive powers of Z are simply suppressed by the limit, and there's exactly one mode which is at the sweet spot of being not divergent and being not vanishing. Good, this is the state correspondent, and indeed this is the first L which is not taken to annihilate the vacuum. So here we see a justification why we should be cautious here. Imposing more L's to kill the vacuum would have trivialized the energy momentum tensor. Would have been a pity to trivialize such a crucial field. Okay, so this was my first example, and here is my second example. Similarly, even though my plan is to not do so much with these oscillators, here is one case that I can't resist showing. These Laurent coefficients of the free boson del X, they are, for a suitable choice of the subscript here, these are the state correspondence to the conformal primary of weight 1, namely this one. And you can, of course, raise the same concern when plugging in the explicit Laurent expansion. Are there many 1 over zeros as I take the asymptotic state and send Z to 0? Well, same logic as over here with the energy momentum tensor. You need a couple of annihilation conditions. Namely, in that case, what you need is that all the alphas with a non-negative subscript kill the vacuum. Yeah, so whenever you are in doubt which modes need to annihilate the vacuum, a quick and dirty way of checking is to compute the state correspondence and checking where you may run into a divergence. But I admit this is not particularly mathematically rigorous. Okay, maybe you were expecting that alpha 0 has a non-trivial action. I think I introduced alpha 0 as the momentum operator 1 or 2 times. And indeed, there's a refinement to the previous statement that there is a modification of the vacuum which is more responsive to alpha 0. So this is, if you wish, my third example for state operator correspondence. These plane waves, which I highlighted as conformal primary fields, if they act on the vacuum, well, let's first of all give this state a name. And it turns out that this is now an eigenstate of alpha 0 with a non-vanishing eigenvalue. So on this, maybe one can loosely call it a vacuum with space-time momentum. On that modified vacuum, we get this vector in the exponent as the eigenvalue. But it doesn't alter the fact that all the higher alphas, now the actually positive modes, they still annihilate that modified vacuum. So if you want to check this yourself, use the OPE of partial x with e to the IPx. There was a simple pole in the OPE of this one with a single copy of del x. Yeah, keeping this state operator correspondence in mind, let's now go ahead and construct the physical states. So for each physical state, there is a field correspondent, and it's the field correspondent with which we will have more fun. So let's denote the field correspondent by VFIS. And this is dubbed a vertex operator, a conformal field equivalent or corresponding to a physical state. Now, how to select good vertex operators, how to formulate criteria on VFIS such that it generates a physical state. So once more, the guiding principle will be conformal symmetry, or whether it's compatible with diff cross Weil invariance. But before getting there, let me once more dwell on the intuition. What is this vertex operator associated with a given state doing? Its job is to insert a closed string state on the world sheet. And the way how it comes across in the first place, well, it's a vertex operator evaluated at a point z. So this variable z refers to a point on the world sheet. So imagine you are lucky enough that the world sheet has genus 0, then it's, for instance, a point on the sphere. And you should always remember that such marked points on a world sheet are morally equivalent or conformally equivalent to an infinitely long tube, which you can think of as an asymptotic state. So this innocent little point is, so to say, the conformal image of an infinitely long tube. And in the picture on the right, it's more intuitive. This is about a state which may come from infinity. And, well, you saw this happening in front of your eyes, this mapping, at the level of the infinite past, where z happened to be on the origin. But if we have conformal symmetry, then being at the origin is not an invariant statement. Not only for the origin in the z-plane, but actually for any point on the Riemann sphere. You can play this game and identify it as the outcome of doing the conformal mapping between this and that. Okay, that is why a vertex operator, also when evaluated away from the origin, should be interpreted as I am inserting a given physical state on a worldsheet. And okay, I just drew it for the sphere to be concrete, but it also works for higher genus. So, as I was saying, the job of these VFIS, these field correspondence of physical states, is to insert that state on worldsheets, and that these insertion points or marked points on worldsheets in general, that they are replacing infinitely long tubes or strips. So tubes, as long as we are talking about closed strings, but to just say it in advance for open strings, then I would draw an infinitely long strip if it was about an open string insertion. And also that is accounted for by a marked point. But we will get to these open string vertex operators separately later this morning. Okay, I hope this gives a feeling of what we will do with these field correspondence, with these vertex operators. But now the pressing question is how to construct or select them. And well, over there, the vertex operator was hanging on a particular point z, and I was already saying it. Singling out a specific point z is not a conformally invariant statement. So fixing some z for the vertex operator once and for all, well, this is not a good idea. Fixing a marked point is incompatible with diff cross while. You can't afford to put the vertex operator on a point and then leave it there forever. So instead, to form a potential diff cross while invariant, you need to integrate over all possibilities where it could ever be inserted. So vertex operator you can view as being covariant under conformal transformations, but in order to speak of a physical spectrum, you want to have the invariants rather than the covariant quantities. And yeah, a neat way of making something invariant is to integrate over the worldsheet. So this is a necessary condition to have a chance to get a diff cross while invariant characterization of the associated state. It's necessary, but not yet sufficient, as we will see. So the advertised move is to look at the integral here, d square z of a given v fizz, and crossing fingers that this is diff cross while invariant. And how to check if it's diff cross while invariant? Well, you do a conformal transformation, and it's clear what happens to the integration measure. You change variables, you just do the usual change of variables when you integrate. So you catch Jacobians from here. And this needs to be compensated by v fizz. It's supposed to compensate this transformation of the measure that I just mentioned. If you want to see it explicitly, that's right here. So what does it mean that v fizz transforms the opposite way? Well, it simply means that it's supposed to be a conformal primary field. It's a pity that I just wiped out the definition, which was more or less here, but what saves the day is to impose the vertex operator to be a conformal primary of weights h equal h bar equal to 1. Then it will just eat up the transformation of the measure, and this integral is diff cross while invariant. Okay, so the problem of constructing the physical spectrum is equivalent to finding all conformal primaries of weight 1. Both H and H bar, please. Yeah, so this is the generality. And we typically want to have the physical states in momentum eigenbasis. At least this is the routine that we successfully followed in quantum field theory. So momentum eigenstates, this was, as you heard at the end of the last lecture, a matter of inserting the plane wave. So it's a safe bet to say each physical vertex operator should be a plane wave times something. But yeah, so let's introduce some notation for all the rest. Everything which is not a plane wave, I will collectively denote by phi-fis. Now, how can I make this a non-vacuous statement if I have a plane wave and a rest? How do I characterize the rest such that you can meaningfully distinguish it from the plane wave? Yeah, so the field X itself is a bit tricky if you don't differentiate it. From the two-point function of del X, which gave a double pole, you can infer that X has a logarithmic two-point function. You must be careful with any undifferentiated X. And it turns out that the exponential is one of the rare cases where an undifferentiated X gives you a beautiful object. But in general, this is not the case. So the big selection rule on this phi, which is all the non-plane wave decoration, the defining property is that only differentiated x's occur. Okay, so what can you do with differentiated x's? And in fact, these admissible derivatives are the field correspondence to these modes here. So if you look at the nth derivative here and put it next to the exponential in the normal ordered package, then you're effectively applying this alpha minus n oscillator. Okay, this is the rough anatomy of each vertex operator. And let's now see how this can be reconciled with the desired conformal weight, h equal 1 and h bar equal 1. So let's bookkeep what the respective contributions are. So for this nth derivative, okay, I need to be careful what I'm saying here. This is by itself not a conformal primary field, but if you succeed to make one, then this will contribute weight h. So more formally speaking, the eigenvalue of L0 for that field is n. So the tentative contribution to conformal weight can easily be stated, even if the individual thing is not a primary field. Okay, I do something similar for the plane wave. Here we even have that additional convenience that the plane wave is a conformal primary. And I reviewed it. Since those contribute something proportional to the momentum square, to both of h and h bar, I can now formulate a selection principle on what the decoration phi-fis is supposed to give. So in order to arrive at a conformal primary v-fis of weight 1, then you want this combination to be 1. But since h phi just can only bring these integer units n of conformal weight, this means that the mass spectrum is constrained and discrete. So remember, these p squares are in fact the negative mass squares of the corresponding states. And actually there is yet another important equation hidden. Note that here we have the same contribution to h and h bar from the plane waves. And what we ordered is a conformal primary of weight 1, 1. So I have two equations for the holomorphic and anti-holomorphic conformal weight. So the decoration phi needs to bring the same amount of h and h bar eigenvalue. So this is what we call level matching. This means that for the closed string, the left and right moving degrees of freedom need to sing the same tune, or they need to bring the same overall contributions to the conformal weight. It doesn't mean that they are exactly identical, but at least they're at the same level with respect to masses and conformal weights. This is the so-called level matching. Okay, so you don't need to distinguish h phi from h phi bar because they are bound to be equal. So now I can give you the formula for m squared. So this connects with what I wrote at the very end of lecture number 1, where you saw a classical mass formula. Maybe you remember the characteristic 4 over alpha prime prefactor for the m squares. And I may have mumbled something like there will be quantum corrections. And here you see it. Out of all that CFT machinery, out of the requirement to be diff cross Weil invariant notion, we found this offset of -1. So since only derivatives are admitted in phi, the conformal weights take values 0, 1, 2, 3, and so on. And hence, the admissible masses, taking that -1 offset here into account, the admissible masses are therefore that discrete tower here. Yeah, and we should by all means look at the trivial case. This decoration phi, well, if it's non-trivial, then it should contain these oscillators, but I can also set it to 1 without violating any rule. So the simplest decoration phi is associated with the lowest m square. Whoop. And what kind of state do you get? This means that m square is -4 over alpha prime. This is an unusual sign for the m square. So the simplest state in the closed bosonic string spectrum is actually a tachyon, defined by having a negative m square. So this is the simplest state as to the construction, but maybe conceptually a very colorful state, because it probably raises a lot of discussion how to interpret a negative m square. I mean, a very naive way to think about it is in terms of special relativity. You might complain, doesn't it mean that it has to move faster than light? This would be a very naive way of looking at it, but perhaps one should take a more refined viewpoint. A QFT way of looking at masses is that m square is essentially the sign of the quadratic term in the Lagrangian. I mean, putting the kinetic term aside, if a Lagrangian for a field phi has a term phi square in its potential, then the mass is the coefficient of phi square. So it's a property of the potential. And there is even a tachyon in the standard model, namely the Higgs field. I mean, the Higgs field is famous for its Mexican head potential, and if you plot the Mexican head potential of the Higgs field like such, then this negative curvature around the origin means that the coefficient of phi square in the Higgs potential is negative. So strictly speaking, the Higgs field is a tachyon. But, well, you all know that LHC measured a positive m square in 2012. So what LHC measured was the curvature at the minimum of the potential. So if we diagnose a tachyon in the string spectrum, maybe we should rethink if we expand it around the correct vacuum. And I fear it's way more abstract and difficult in string theory to transition between here and there than it is in the Mexican head potential of the Higgs. So the right way or the right formalism to do that is string field theory, and I would refer all the questions to Carlo about this fascinating subject. Okay, there is a tachyon. Let's for the moment note that it's the only state with negative m square. And spoiler, when we do the analogous construction for the superstring, then we won't find a tachyon. Good. This was a first look at the spectrum, or this was formulating the rules. We are supposed to construct conformal primaries at weight 1, and the tachyon can be immediately written down, but as soon as you put in some dx's, where is the formula? It's gone, of course. As soon as you take a non-trivial decoration that you adjoin here, you must be really careful that you preserve the conformal primary condition. So identifying the physical polarizations requires some care, and I will illustrate these challenges through the massless level. Yeah, so a lot can be learned from the m square equals 0 case, which is, from the viewpoint of the decoration phi, the next to simplest case, where we order 1 unit of conformal weight rather than 0 units of conformal weight from both the left movers and the right movers. So what's the most general combination of such fields in phi? Let's make an ansatz for them. The only thing I can do with 1 unit of conformal weight contribution is this one for the left mover and that one for the right mover. And they inevitably bring 2 Lorentz indices, which I must soak up. So here I'm introducing a formal polarization tensor whose job it is for the moment to soak up the indices, but we will see how to interpret them physically. So here this is a rank 2 polarization tensor compatible with the Poincaré invariance of the bosonic string. So it's a tensor of the Lorentz group SO1, D minus 1. So capital D is still arbitrary at this stage. Okay, now assembling the complete vertex operator as the normal ordered product of this and a plane wave, we now need to check, is it really a conformal primary? I mean, we did some preliminary filter not to screw up the H, but it's not at all clear whether this is a conformal primary. Yeah, maybe I should write it again, that what we are now looking at is these fields together with the polarization inserted into this normal ordered product. And now the moment of truth is when we hit it with the energy momentum tensor. And it turns out not all choices of zeta are good enough to do that. So let's say we are doing this OPE calculation with a random zeta. Then what you find is, well, you would prefer to now find double pole and simple pole as demanded for primaries. But as a sad fact of life, what you get is a triple pole, which is not part of the protocol, and the numerator turns out to be this tensor contraction where P goes together with zeta. Yeah, and the pole residue, well, it's not so essential what it is, but let me just state that the pole residue is non-trivial, so no way of arguing that this is irrelevant. And well, of course, there are also double pole and simple pole present, but I don't need to look at them if my goal is to construct a conformal primary. Since if this term survives, then we are screwed. Okay, so clearly we must ensure that this triple pole here vanishes. So as a necessary condition on the polarizations to describe a physical state is that this tensor contraction has to vanish. So here, this is an obstruction to conformal primary condition, and hence an obstruction to physicality of that state. Okay, so we need to impose that this polarization tensor is transversal, that it's contracting to zero with the momentum, or you may say it's perpendicular to the momentum. And okay, this is the meromorphic analysis hitting with T, and there's an analogous equation if I hit with T bar instead. So the analogous T bar equation concerns contraction of the second index with the momentum. Good, so these are physical state conditions that we should urgently impose. And in the bigger scheme of things, this illustrates here the following. If you have conformal primary A, and you take a normal ordered product with conformal primary B, you will in general fail to get a conformal primary. There is no simple composition rule. I mean, maybe some of you got very hopeful when noticing that this phi by itself happens to be a conformal primary, but this is not buying you much. I mean, the issue is that the energy momentum tensor is bilinear. It has this dx times dx. So there is a term where the two dx's of t are distributing, one hitting the plane wave and one hitting the decoration. So it's because of these kind of cross terms that the conformal weight property is not multiplicative under normal ordered products. So all this to say, you will unfortunately not be safe from doing this exercise here. At some point, when you want to filter out physically meaningful polarizations, you will have to evaluate the OPE with T. But okay, here we found a condition. We found two conditions on the admissible polarizations zeta. It seems like we can make progress in counting the physical states. So without knowing about that constraint here, you would have said d choices for mu, d choices for nu. You could have expected d square states before we found that physical state condition. And now that we are demanding these contractions to vanish, it simply means that zeta shouldn't have any components in the p direction. Just think of p as being just one spacetime direction, and that one we have to clip off. So naively, you have d minus 1 square solutions. So d minus 1 for the values of mu or nu which are not in the direction of p, or which are perpendicular to p. So this is the number of solutions. So these are the candidate physical states. No, I mean, they are all physical, but some of them turn out to be boring. Some of these solutions, even though they yield primary fields, some of them turn out to decouple. Decouple in the sense of having vanishing amplitudes with everyone. More precisely, some of them give you total derivatives for the vertex operators. Suppose you have a total derivative for the VFIS. Oops. Then the conformally invariant combination formed from its integral is 0. And there are two ways of being 0 in that sense. If it's a holomorphic derivative or if it's an anti-holomorphic one. In both cases, that vertex operator integrates to 0 when we integrate over a closed string worldsheet which has no boundaries. Okay, it's a dangerous statement to say this. Even for closed strings, there are certain caveats and extra conditions. But with some extra subtlety discussion, one can make this more rigorous, that total derivatives integrate to zero. And hence, this may be a this may be conformally invariant, but it's boring. It has a null state, so to say, a zero norm state. And the nickname for those is spurious states. Okay, so what we really care about, what are the physical states that are not spurious, that are not decoupling, which are giving rise to non-trivial physics? Okay, so this is, of course, an abstract argument applying to all mass levels, but let's now specialize this discussion to m squared equals 0. So which solutions of these conditions are spurious? And I will do it in the unfair way. I just write down the answer, and it's easy to check that this is spurious. I just construct total derivatives, which occur among the m squared equals 0 states. So at a given mass level, you need to smell what are the correct primitives, such that the total derivatives are talking to the solutions you're looking at. So how do I generate dx d bar x from a total derivative? And the right primitive to do that is of this schematic form here. So it's essentially subtracting 1 unit of holomorphic conformal weight h to get the w, and subtracting 1 unit of h bar to get the interesting w bars. Yeah, so let's now compute the total derivative using the chain rule. So the d bar x is anti-meromorphic, so the derivative only hits the plane wave, the holomorphic derivative. And what we get is, by chain rule, momentum contracting the partial x, the partial zx, and then I just copy-paste the partial z bar x. So now, indeed, this was a good choice of primitive w. Upon taking its holomorphic derivative, this lines up with the states we have in our ansatz for massless polarizations. Okay, let's convert it into a concrete polarization tensor zeta. So lining this up with the general form of the ansatz means that a spurious polarization is of this form. And of course, I could have played the same game with the role of z and z bar interchanged. So yet another spurious polarization choice is put the mu index on some vector psi and the nu index on the momentum. Yeah, both of them are spurious states. And if you furthermore demand that they are physical, then don't forget to impose that these vectors psi are perpendicular to P. Okay, in summary, not all of the solutions to the primary condition are non-trivial as physical states. A few of them have zero norm or decouple or are called spurious states. No matter which terminology you prefer, mod out by all total derivative vertex operators. Let's see, we should make a break soon. Yeah, maybe I just finish the counting and then we make a break in 1 or 2 minutes. Yeah, as I was saying, at the moment of making the ansatz, there were d-square candidate states in the game. After imposing these transversality conditions, the counting dropped to d minus 1 square. So let me give the last step. How many states survive after modding out by spurious states? Subtracting those which we generated from total derivatives of W or complex conjugates. So the final counting is d minus 2 square solutions, which satisfy everything on our wish list, that it is a conformal primary, that the obstruction vanishes, and furthermore, that it is non-spurious, that the polarization tensor is neither of this form or of that form. And the answer to the counting problem, how many such zetas exist, the answer is d minus 2 square. And there are various ways to think about this. At a highly pragmatic level, you could just say, maybe there are 2 space-time dimensions less than you think, which do the counting of physical states. I mean, it was very manifest that here we were discriminating that space-time direction where p is aligned. We don't want to have components in p direction. And now here, with the subtraction of spurious states, it's a similar story. We are forbidding longitudinal components. So it's also like subtracting off one space-time direction. Please take this with a grain of salt, or it's nothing I can say in a Lorentz covariant way. But as far as the counting is concerned, you get away by pretending that space-time has 2 dimensions less. And this can be made very precise if you go for so-called light cone quantization, which is, for instance, neatly presented in David Tong notes in a very early section. So the idea in light cone gauge is to not even try being Lorentz covariant. To early on get rid of 2 spacetime dimensions. This has to do with making a particular choice of residual gauge freedom and solving the Virasoro conditions for one of the spacetime directions. And yeah, in this light cone business, you are making it super manifest. So in light cone, one would just recognize that by saying, I only have these oscillators here at the m square equals 0 level, and the indices I and j have a reduced range of d minus 2. So if all you wanted to get out of this lecture is the number of massless states, you would have been better off with the light cone approach. And to me, it's important for me to give you a covariant description of the spectrum, and also to do this in CFT setup, such that we can swiftly move on to aspects of the superstring and to scattering amplitudes. So if you have follow-up goals, what you want to do with these physical states, then there are certain drawbacks to the light cone formalism. But I would nevertheless encourage you a lot to read through this section at David Tong. It's very neatly written, and it has a beautiful derivation of the critical dimension. Yeah. So here, things are not in the light cone framework. Good, let's have a break. Yeah, welcome back. Hope you're all freshly coffee-inated. Let's go on discussing our findings here among the massless states. From the discussion before the break, we saw that there is one non-trivial physical state for each rank 2 polarization tensor, which is first of all perpendicular to the space-time momentum, and which is secondly not of that form where one of the indices is hanging on P, on the momentum. Now, what is the kind of physical role that these states play? The physics of massless states, in order to extract that, the 0th order exercise is to disentangle the quote-unquote particle species. So similar to how particles are defined in QFT, the most basic move to do before discussing any type of physics is to decompose into Lorentz irreducibles. I mean, irreps with respect to the Lorentz group in the respective space-time dimension. So with the rank 2 tensor, there are exactly 3 irreducibles. The first one is symmetric and traceless. I'm not sure how standard it is, but I saw many friends writing an angular bracket when trying to say symmetric plus traceless. And then there's an antisymmetric part, and then finally there is a trace part to it. Okay, and the most important one to connect with physics we know is the first one, this symmetric, traceless, irreducible. And this turns out to be the graviton for reasons I will explain in the next minutes. But just to see what else we have, here there is an anti-symmetric combination of dx and dx bars. So this is giving rise to a two-form polarization. And well, I don't expect you to have seen that in, say, particle physics, for instance. So this is a, so to say, new massive state of the string, the so-called B field or Kal-Bramont field. And this is, for instance, interesting when you compactify strings on a circle. This field couples very prominently to winding modes. So these are intrinsic to the string and have no particle physics analog. And also from a mathematical point of view, it's a beautiful generalization of a gauge field. If you use differential form notation, then you can write a photon as a one-form potential with a scalar gauge symmetry and with a two-form field strength. And if you repeat all of these equations to characterize Maxwell with one more index, with a higher form degree, then you can describe the B field, which is a two-form as its polarization, which enjoys one-form gauge symmetry, and which furthermore has a three-index field strength that we can use to describe its low-energy interactions. But it's hard to say more concrete things about the B field at this stage, so let's just keep in mind this is yet another massless state next door to the graviton. And then as to the third Lorentz irrep, this is the trace. I should add some qualifiers. It's not as simple as taking the trace with the d-dimensional Minkowski metric, but you need to take the trace in a way that preserves these properties. So let me just put a coward perp symbol here to remind you that there is some bells and whistles to how the trace is taken. Same bells and whistles here. Okay, and this trace is corresponding to yet another particle species. It's a scalar, and it's known as the dilaton. So in a loose sense, this is a trace counterpart to a space-time metric having to do with how you measure distances in space-time. And its most important role for string perturbation theory is that it will acquire a vacuum expectation value that sets the string coupling. I was showing off in lecture number 1 that string theory has very few free parameters. And for sure, there is no extra parameter for the string coupling, because this is a matter of finding the vacuum expectation value of this scalar field, the dilaton. Okay, so these are 3 particle species, but I will really focus attention on the graviton here, or try to argue in more detail why the symmetric traceless part of this vertex operator should describe a graviton. And here, the spurious states are actually quite helpful to illustrate a key property that defines gravitons. Namely, suppose you want to add the spurious state. I mean, the spurious state is morally zero, so it's never wrong to add it. You won't change anything about the physics. And what do you do to the polarization when adding this spurious state? Well, you shift the polarization by this symmetrized outer derivative here. So we are in the traceless symmetric part, hence the symmetrized combination of p mu psi nu, and furthermore, physical state condition requires psi to be perpendicular. So this is a gauge freedom to the graviton polarization, and I very much hope that you have seen this before last week. This is nothing but a linearized diffeomorphism. If you do perturbative GR, if you expand your space-time metric around a given background, then this is the linearized contribution from a diffeomorphism. So after all the diffeos on the worldsheet, here is finally an example of a space-time diffeomorphism. Okay, now what properties have we assembled from only worldsheet arguments? We have seen that there is a symmetric traceless Lorentz tensor, I mean spin 2 in colloquial terms, and that spin 2 polarization enjoys a diffeomorphism invariance. This is already enough to say conclusively this is a graviton, because there's a kind of uniqueness to graviton. Being spin 2 and having this linearized diffeomorphism symmetry, that's enough to build up GR if you look for a consistent nonlinear extension of all of that. So from these very basic observations, it's already clear that this massless closed string excitation must be a graviton. It, of course, doesn't tell you what kind of higher derivative corrections there are to Einstein gravity. It also doesn't tell you what kind of additional states will couple in pairs to the graviton. But just for the basic properties of the field, this is characterized to be the graviton based on having spin 2 and diffeomorphism in variance. Yeah, so in that sense, it's unique that this must be a graviton. Okay, this is a first way to argue that it's a graviton. There's also a second way, an alternative argument, in case you don't find this particularly compelling. What if you dream about a Polyakov action extended to curved space? Whoops. Okay, if you were to speculate, how would you write down an analog of the Polyakov action which is adapted not to flat Minkowski spacetime, but to, well, generic spacetime at a non-trivial metric tensor? What we have so far in the Polyakov action is this one. I mean, I took the liberty to switch the conformal gauge version into Z and Z bar coordinates. And traditionally, we were contracting that with Minkowski metric. But if you were asked to guess what the curved spacetime analog is, I guess you would be fiddling around here and replace Ada by a more general spacetime metric. And this is the ambitious task of generalizing to, well, completely different background. You can also ask the more modest question, how do you deform away from Minkowski? So you can do this perturbatively and say, let's take this metric tensor to be reasonably close to Minkowski spacetime. Then the fluctuation is essentially the graviton vertex operator. Yeah, I mean, contracting this with something traceless symmetric, H, This is exactly the graviton vertex operator. And in path integrals, you find the action in the exponent. So in path integrals, you would find an exponential full of graviton vertex operators. And that in turn means path integrals automatically give you coherent graviton states. Not just a single excitation. I mean, a single graviton does not make space-time interesting, but you need infinite numbers of them, or coherent states formed by certain exponentials of the graviton oscillators. Yeah, so argument number 2, why this should be thought of as a graviton, is that in the Polyakov action, a naive curved spacetime generalization will automatically involve the graviton vertex operator that we constructed. Good, that's everything I wanted to say about the massless states for now. I will next give a mini overview of the massive states, unless you want to ask more about this. Okay, so the rules, I more or less stated the rules before the break. The rules to construct the rest of the closed bosonic string spectrum, that infinity of extra states, the rules are as follows. We saw the general formula for the mass square, that what matters is how much conformal weight do you put into this decoration phi, which is accompanying the plane wave in the vertex operator. And yeah, this h phi, it counts the number of derivatives. It counts both the number of partial z's and the number of partial z bars. So as I stressed before the break, we have this level matching condition. I mean, the plane wave is democratic and gives the same amount of h and h bar. And also our target is democratic in the sense that both h and h bar should be 1 in total after combining plane waves with the decoration. So hence the derivative count is always the same in the decoration at each mass level. And the simplest positive mass square state you will find by, well, going one derivative count higher than we did at the massless level. We used to do h phi equal 1 for massless states, but if you want to see a positive m square, then this is the simplest value to pick. And then the corresponding p square goes like that. Yeah, so you would again start with an ansatz if your task is to give all the polarizations at the first mass level. And what you would do is, well, you write down everything which has the correct derivative count. And if the total number of derivatives is 2, then I can go either for this one, where 2 different x's get 1 derivative each, or you just put a double derivative on one of the x's. And this was just about the holomorphic ones. I mean, I still need to do similar moves with the z bar derivatives, and a priori this could be associated with an independent Lorentz index. So yeah, you can see that these massive states, they gather more and more Lorentz indices. So this is just the ansatz, and similar as before, we need to play this elimination game, that we first need to find the physical state condition by hitting it with T, by checking that the OPE with the energy momentum tensor has nothing worse than a double pole. And you are realizing the step 1 in the curly bracket. And in the last round, you check for spurious states, like pure descendants with respect to the conformal group, or in the simplest case, total derivatives that need to be modded out. Yeah, doing all these things explicitly and covariantly requires a bit of skill in manipulating many Lorentz indices. So here in that concrete case, you have polarization tensors, well, of different rank if you go between double derivative and 2 single derivatives. So you need multiple polarization tensors with between 2 and 4 indices. And yeah, there are constraints that you can derive in a systematic way by imposing the primary condition with respect to both the meromorphic component and the anti-meromorphic one. Okay, so this is how you would proceed. And if I remember correctly, the answer for, say, the left movers, it's enough to look at the traceless symmetric part here, and you can completely gauge away that. This is admittedly not obvious if you start the calculation, but if you grind through it, then you will find that all of those can be absorbed into spurious states. And then the physical state conditions give you the license to take the polarization here to be symmetric traceless. But this is just the meromorphic half. It still remains to do the same here and tensor them together. So you nevertheless have a rather rich representation theory. And maybe you can smell from this representation theory due to the tensor product of left and right that the open string will have a somewhat simpler spectrum. Or at least, as you will see after the break, or maybe even before we make a next break, that in the open string analog of these constructions, there is just one derivative species. There won't be any need to distinguish Z and Z bar, and that certainly simplifies life in many respects. But okay, we are still in the closed string discussion. I can't help writing down the state correspondence of all these vertex operators we found, and in passant point something out about the spins in space-time. So clearly from what you heard today, the tachyon has a state correspondent which I wrote down before like such, which was the asymptotic state associated with a naked plane wave and nothing else. So this was having a good eigenvalue with respect to the alpha 0 oscillator. And everything that goes beyond the tachyon, well, the alpha 0 oscillator is diagonal. The alpha positive oscillators kill that state. So everything else must be alpha negatives. And this is the more traditional way of constructing the states. But of course, you need to work hard to get the physical state constraints correct. Yeah, so this partial x bar, which gave rise to graviton, B field, and dilaton, this has a state correspondence like such. So I'm just repeatedly using the fact that the nth derivative of x corresponds to the alpha minus n oscillator. So the slightly more bulky ansatz at the first mass level from over there, this translates into these oscillators. From the left mover untwiddled alphas, from the right movers twiddled alphas. And yeah, no matter whether you use the field or the state description, not all of the states I'm writing down here are physical. You need to do the usual projections to those which are compatible with conformal primaries. Okay, if you go on with that for an arbitrary mass level, let's say I aim for capital N as a h phi as the conformal weight of the decoration, then you can anticipate that will be a collection of alpha minus 1 only. So if I violently want to maximize the number of oscillators and therefore the number of Lorentz indices, I can immediately point out that this will be part of the states. Put as many pairs, alpha minus 1 and alpha twiddle minus 1, put one such pair for each unit of mass level. So this will be part of the state content. And given the multitude of Lorentz indices, this has a very high spin with respect to the Lorentz group. So for mass level n, it goes all the way to spin twice capital N. And the maximum spin at a given mass level comes from here. But of course, there is a huge tail of lower spin states. I mean, example is, for instance, here, that two tensors coexist with vectors. And all the coexisting states with higher oscillator numbers, that's giving you a more and more sophisticated tail. But here I'm just talking about the highest spin state at a given level, and I can slightly rearrange and solve for the maximum spin as a function of the level, or equivalently as a function of m squared. So if you set m squared to 0, then we saw a spin 2 state, namely the graviton. And if you admit positive m squared, then the spins will grow like that. More precisely, the maximum spin seen at a given level. And these kind of relations between spin and m squared, this gives rise to the terminology for alpha prime that I briefly mentioned at the beginning. So alpha prime is here the slope of this j versus m squared plot. So that's the reason that alpha prime is sometimes called the Regge slope. Or at least these arguments justify the word slope in the spin m squared plot. More precisely, open and closed strings will have a slightly different slope, differing by factors of 2, but this definitely conveys the general gist. Okay, a last remark on all the discussion of spectrum. Last remark is about negative norm states. Maybe you got a bit intimidated by this process of computing OPE with T and formulating the physical state constraints, but this is very, very important to have unitarity on board. So all these conditions on the polarizations, they remove negative norm states. So already for the graviton, one can go through this explicitly, and the same reasoning applies to the massive analogs of these polarizations. This primary constraint kills the negative norm state, every negative norm state. I mean, maybe you remember this in the context of QED. If you quantize the Maxwell theory covariantly, and if you're not careful about constraints, then you may worry that you have negative norm states, or the inner products among certain tentative states involve a Minkowski metric with indefinite signature. And exactly the same issue arises here. Say, if you look at such a state and compute the norms for all of these states with various mu's and nu's, then there will be many negative norm representatives. I mean, there will be some factors of Minkowski metric if you compute the inner products among the massless states. Yeah, and the physical state constraints is exactly the salvation to kill everything which has negative norm. And I'm formulating things in a way that this is done covariantly. I mean, a naive way of removing negative norm is to take out the time direction, but this is not at all Lorentz covariant. So what we are doing here is the Lorentz covariant way of removing negative norm states. So please be aware, this is not just some cosmetic fine-tuning, the physical state conditions. This is bare necessity to keep unitarity alive. So all physical states in the string spectrum have non-negative norm. Worst case is that you have zero norm like the spurious states. Okay, it's probably early enough that I can seamlessly go on into the open string discussion. That's all for the moment, what I wanted to say on closed strings. Next move is to discuss open bosonic strings, along with a short dip into D-branes. And starting point of that discussion is the need for boundary conditions and the two prominent choices known under the name Dirichlet and Neumann. I guess I will be lazy and write capital N and capital D when referring to Dirichlet and Neumann. Yeah, as I briefly mentioned at the beginning of the course, for open strings, you track their propagation in space-time through worldsheets that now have a boundary given by the world lines of the endpoints of an open string. And the conventional parametrization of these open string worldsheets is through a spatial coordinate sigma that is not periodic. So you put the endpoints at sigma equals 0 and sigma equal pi. What used to go all the way to 2 pi for the closed string is now cut off at pi with no periodicity imposed. And yeah, we take a non-periodic spatial coordinate sigma in this range here. And we want to recycle the Polyakov action. The good thing about Polyakov action is it's completely insensitive to what kind of worldsheet topology there is, whether it has low genus or high genus, whether it has boundaries or not, regardless of how many boundaries there is. So it's still the Polyakov action that makes the music. And we were at some point varying the Polyakov action or its variant in conformal gauge, and we were rather careless about boundary terms. I mean, Polyakov action was having del x, and we converted this to a field equation of the form del square x. There was an integration by parts involved, and in closed string case, it was okay to do this without boundary terms. But now, for open strings, we have to revisit this analysis, how to avoid that boundary terms hop in and spoil all the analysis based on varying the action. So what are these potential boundary terms, and how do we ensure that they are absent? Yeah, if you do this variation carefully in conformal gauge, then the starting point is that by chain rule you have twice the alpha derivative of the variation, contracting another alpha derivative without variation. So this is essentially the opening line. And as I said before, in order to derive the free wave equation, it remains to move this derivative over to the other side. So this is what I meant as integration by parts. So let's look at how this goes in all detail. So there is the term that I want to see to get the wave equation. This is the term we were processing in all detail for closed strings. And now the surface term, which may or may not be there, well, I'm already converting the total derivative into this dn, which I will define shortly. I'm not sure which notation you were using in your undergraduate courses on vector analysis or electrodynamics. I grew up with a notation like dn alpha, which refers to an outwards pointing normal vector. So to dissect the boundary terms carefully, let's introduce some initial time and some final time for that worldsheet. Even though we will eventually send them to infinity, it's probably good for all of us to have a finite piece of area to stare at. And what I meant before with this dn alpha, it is when we go along the boundary of the worldsheet, this dn alpha is the outwards pointing normal vector like here. So depending on whether I'm on a time-like or space-like boundary segment, it is either in tau or in sigma direction. Okay, so as I said, the first term is okay. This is what we want, and this is what we know how to deal with from the closed string. And it is this additional term, only for open strings, that I will process further. Good. What is this tentative boundary term with the above explanation of the dn alpha? So let's go over the 4 contributions to that. I mean, that piece of open string worldsheet in the above figure, it has 4 boundary segments. 2 of which are extended in sigma direction and happen at fixed time. So in the notation of that figure, this fixed time is tau final and tau initial. And here the outwards pointing normal is in tau direction. So just look at the arrow that points downstairs. So this is in tau direction where it points. And down means that I have to put a minus sign here. So this is covering 2 out of the 4 boundary segments. And then the other one is, well, here the boundary segment is going in tau direction, and the outwards pointing normal is in sigma direction, so hence you here see a sigma derivative. And of course it is evaluated on the extremal configurations of sigma. It is namely part of the world line of the endpoints. Okay, and once more, there is an easy part and there's a hard part. By easy I mean that it was just an artificial idea to introduce an initial and final time. Of course, in practice, we think of these as being at plus minus infinity, and we always pretend that in infinite past and future, everything is settled, and that we don't even think about having variations at infinite past and future. So please don't worry about this term. Namely, the real deal is to see what that piece here is doing, or this is where we need to impose by hand some vanishing condition for that term. So it is this piece here which inspires our choices of boundary conditions. So these open string boundary conditions, yeah, they are the answer to the question, how can I stop this integral here from contributing? Because this would spoil the variation process of the Polyakov action. At least we would have to stop dealing with the free wave equation. Okay, and there's a separate boundary term, both for sigma equals 0 and for sigma equal pi. So strictly speaking, you have independent choices to be made at these two open string endpoints. You want that a product vanishes, a product of variation and sigma derivative. And of course, to get a product to vanish, it's sufficient to have one of the factors to vanish. So depending on whether you make del x vanish or its sigma derivative, this is either the Dirichlet or the Neumann boundary conditions. Yeah, so in the case of the sigma derivative, this is Neumann, maybe the last time I'm not using the acronym. Here you impose that in some space-time direction xa that, yeah, this sigma derivative vanishes at the endpoints. Okay, here, negatively speaking, I impose a constraint. Positively speaking is that I don't constrain the position of the endpoints. So the endpoints can still move freely. So that for the positioning of the endpoints, Neumann is less constraining. Okay, and why am I using A in the place of where you expected a Lorentz index? So the idea is that you can make different choices for different space-time directions mu. So here I'm not scanning through all the values 0, 1, dot, dot, dot to d minus 1, but I'm introducing a global parameter p that counts the number of Neumann directions. Or to be even more precise, Neumann directions are always imposed in x0, in the time-like direction, and then among the many, many spatial directions, pick your favorite number that is a Neumann boundary condition. So we have Neumann conditions. So P is the number of spatial directions where Neumann conditions are imposed. So it has nothing to do with momentum. I just realized that I'm overloading the letter P, but in the next 10 to 20 minutes, P counts the number of Neumann directions. Okay, so A is, if you wish, a constrained Lorentz index, which is only on tour in the Neumann directions. Yeah, after Neumann comes Dirichlet. The other choice to make this decouple is to set the variation to 0. That I make a rigid choice. The x in a given direction is at the origin or is at some position C or D that I'm describing by hand. So this is going under the acronym D, Dirichlet. And here the endpoints are not moving freely. Here the respective endpoints are fixed. And I already confessed that in time direction I really want to have Neumann and not Dirichlet. So let's say they are fixed in space rather than fixed in space-time. Again, I use a different type of index, no longer mu, because mu is always going through all the space-time directions. But let's use capital I whenever we refer to the Dirichlet directions. So here is the same little p that counts the number of spatial Neumann directions. And here is the range where the Dirichlet configurations of the Lorentz indices can be. Yeah, just to have a clear variable name and a clear statement of the condition. So for the first open string endpoint, the one that I'm describing by sigma equals 0, I prescribe a vector ci, where that open string endpoint is, and it is there for all proper times. So the entire world line is fixed. So the time evolution is stopped for that endpoint. And the analogous notation for where the other endpoint is fixed is at little ci. And Dirichlet condition requires us to make a choice for some ci and for some di. I'm sorry? It is not impossible, but it's a slightly more exotic case. It is known as an instanton, something that happens in a given moment of time. Let's say it's part of the bigger game of string dualities, but I like to keep it as a special case. At least it's harder for everyday life intuition. How do you stop something from propagating in time? If I have a rope, I can of course hold the endpoint fixed and keep it fixed in a spatial direction, but I have a harder time stopping an endpoint from moving in time. Good. For each value of the Lorentz index, we impose either one or the other. So this is clearly sufficient to make all these disturbing boundary terms go away. And then this means that we can classify the degrees of freedom in a similar way as we did for the closed string, namely by studying the mode expansion, which is compatible with the free wave equation. So step 0 towards the open string spectrum is, we have ensured that the wave equation comes out in the same way as for the closed string. So now study the classical solutions to the wave equations and make sure that you impose the boundary conditions. So whenever you see the mu index, it's collective for both of Dirichlet and Neumann directions. So it's both A and I at the same time. Yeah, in the analogous moment of the closed string discussion, I was pointing out that there is periodic boundary conditions, back then for closed strings. Of course, this is no longer the case. So now that we are describing open strings, we don't care how sigma is related to sigma plus 2 pi. So this periodic boundary condition is gone, and replace it by Dirichlet or Neumann conditions. Okay, so this will change the nuances of how we organize the mode expansion. What doesn't change is the ansatz, the splitting into left and right movers. So regardless of the boundary conditions, the cheapest way of solving the two-dimensional wave equation is to pick light cone coordinates. Maybe I should have written z and z bar to stay in touch with all the complex analysis, but maybe it's even easier for you to compare with the closed string situation if I, for the moment, roll back to sigma plus and sigma minus. Okay, many things go through, namely the oscillator tower will go through, and there are minor changes in the zero mode sector. So maybe it's enough if I write down the zero mode sector for you. There is first of all a different factor of 2 here for the momenta, or if we want that there is an interpretation in terms of space-time momentum, then the reduced range of sigma translates into different factors of 2 right here in the linear terms. But more exciting than factors of 2 is that now we admit different p left and p right. So in the closed string case, the periodicity was making it clear that we shouldn't have a linear dependence on sigma. This was a no-go when periodicity is imposed. But now that this is relaxed, now we can consider P left and P right that are different from one another. Okay, and now there are these oscillators, and it's literally the same as in the closed string, so I won't write it out. This is, again, the alpha and alpha twiddle oscillators, literally the formula from the closed string. Yeah, what are now the implications of Dirichlet and Neumann? So if you plug these mode expansions into the boundary conditions, then in the Neumann case, you find that these momenta still want to be the same. P left still wants to be the same as P right. And furthermore, from the vanishing sigma derivative at the endpoints, you find that the alpha oscillators are glued together. So in all the Neumann directions, alpha and alpha twiddle are identical. I mean, clearly you want the boundary condition to be true at all times. And being true at all times means there is a separate equation for each Fourier mode. So don't be surprised that there is an infinity of conditions. And if you do the analogous Fourier decomposition of the boundary condition for Dirichlet, then what you find is that even the center of mass position is now getting fixed. So the xi, I mean here little x, the first term, is fixed to be the first choice of endpoint. And there's something really funny about the P left and P right. They are now opposite to each other. And, well, they just ensure that we interpolate between C and D as sigma is dialed from 0 to pi. So it's actually something very simple like that one. It's a bit like solving a linear equation system for two unknowns with the goal that the zero-mode sector here reproduces the values Ci and Di at the endpoints. Yeah, the Ci and Di are defined up there, the third line of the upper board. Okay, so all of this is what you find for the zero-mode sector, and then Fourier non-zero modes. This again interlocks the alpha oscillators, but now with a relative minus sign. Okay. Yes, please. Absolutely, yeah, indeed. Here I'm just discussing the boring cases, combining Dirichlet with Dirichlet and Neumann with Neumann. It's quite exciting to look at the scenario where you mix, like Dirichlet on one endpoint, Neumann on the other endpoint. I mean, all we need to solve is the vanishing of these boundary terms. Indeed, having a cocktail of Dirichlet here and Neumann there in the same space-time direction, that works. And the interesting implication is that the alpha oscillators now get a different moding. Instead of integer Fourier modes n, in Z, you get half-odd integers, n equal a half, 3 half, 5 half, and so on. Yeah, this is quite juicy, the mix of Dirichlet and Neumann. Yeah. Yeah, sorry that I'm not proactively covering that. Yeah, in these homogeneous choices that for a given space-time direction, we have both endpoints in the same style of boundary conditions. What's the common conclusion here? The oscillators which govern the construction of the spectrum, these oscillators are interlocked. There is no more room for independent alpha twiddle. I mean, this relative sign is immaterial when it comes to degree of freedom counting. So here you see the reason for my earlier claim that open string spectra no longer distinguish between Z and Z bar. So in comparison to the closed string, only one oscillator species. And you saw before, in case of closed string state construction, how the two species of oscillators give rise to a very rich representation theory of the Lorentz group. One oscillator species only. This is true for both Neumann and Dirichlet. Yeah, last thing I want to say before the break is the classical mass square formula. So how did we get it before for the closed string? Well, on top of the equations of motion, for x, we also have to obey the equation of motion for the metric. Okay, you didn't really see the metric. I was working in conformal gauge to settle the mode expansion of x, but also in the open string case, there is the energy momentum tensor on the worldsheet, actually in the same functional form. And also for open strings, you have to impose the vanishing of the energy momentum tensor. And we got a formula for the m squares from its zero mode. I mean, you can do a Fourier expansion of T alpha beta in the same way as you Fourier expanded X. And it was in the zero mode of this energy momentum condition that we could extract the formula for m square. And well, strictly speaking, m square, it only has contributions from the Neumann directions. I mean, here, even though we interlocked P left and P right, it still gave you the freedom to choose one of them however you like. So there is still room for a momentum degree of freedom in Neumann directions. But not so in Dirichlet directions. I mean, both P left and P right are already determined in terms of the data, Ci and Di, that are imposed. So no more room for a momentum. This only has contributions from Neumann directions. But on the right-hand side, there is something funny. On the right-hand side, we find a mass contribution from the Dirichlet directions, namely the displacement of the two endpoints. How far do we stretch them in the spatial directions where Dirichlet conditions are picked? So the full formula for the m squares at classical level goes as follows. So this is reminiscent, the last term is reminiscent of the closed string case. I mean, we saw before the break that this will later on amount to an integer quantization of that thing. And we get the alpha oscillators in both Dirichlet and Neumann directions. And in comparison to the closed string, there is now a factor of 1/4. So note that we used to have 4 over alpha prime in the closed string case, but the open string spectrum is stretched. Okay, so different factor of 4 normalization of the entire mass spectrum. And now, finally, let me comment here on this exotic term, which has no closed string analog. And this means that there's an extra contribution to the mass proportional to the stretching. Why do I say proportional? Well, it's an m square formula. So solving for m alone, the mass will grow linearly with a separation of the endpoints. So as I said at the beginning of the course, it is not a Hooke law where the energy of a spring grows quadratically with the way I stretch it, But in the string case, there is a linear growth of the energy slash mass as I pull the endpoints further apart. So there is a linear mass contribution from the displacement of the endpoints from the spatial stretching. Yeah. The further discussion with boundary CFT and all that, we better do after the break. Shall we now do a longer break?
Yeah, now it's time for the long break.
Okay, yeah. 20 minutes.